Okay, so in the first video for chapter 4, we looked at how you could use the equation, you could use the derivative to find the equation of the vertex of a parabola. And that was pretty simple. And so then we're going to take it up a notch and we're going to look at cubic polynomials. And so what I'm going to do is I'm just going to say, let's take a cubic polynomial. And so I'm going to break it into 3 parts. I'm going to say that it crosses the x-axis at negative 1, positive 2, and positive 3. So there I've got my cubic polynomial that crosses at negative 1 because of that, positive 2 because of that, and positive 3 because of that. And so I'm going to sort of FOIL that out. I'm going to do x squared minus x minus 2 times x minus 3, and I get the same thing. And then I'm going to go y equals x cubed minus x squared minus 2x minus 3x squared plus 3x plus 6. And then I'm going to combine terms in there, so it's going to be x cubed minus 4x squared, take this term out, plus x plus 6. And I should get the same function. And I do get the same function. So basically the point is that this is sort of where I got this from. So I just sort of said, well, I just arbitrarily want it to cross at negative 1, positive 2, and positive 3. And so that's kind of where I started from. But let's work with this one. Suppose we don't know anything about this. There's ways that you can sort of deal with this, but calculus is a very powerful way to deal with it. So let's graph that. And I want to know where this point is going to be and where that point is going to be. Where's the max and where's the min? Well, in calculus, the max and the min and min are where the derivative equals 0. So why don't we just take the derivative? It's pretty easy. Y equals 3x squared minus 8x plus 1. Now let's not even try to factor that. Let's just plug it into minus. So we got 8 plus the square root of 8 squared minus 4 times 3 times 1, all that to the 0.5 power. So I'm just doing quadratic equation is what I'm doing. And let's put that in a set of parentheses and divide it by 2 times 3. And so I get that one of the places where my derivative is equal to 0 is 2.53518. And I go over here. And it says right there 2.53518. There you go. And so then if I just take that and plug it right back up into my original. This is going to be sort of a pain, but we can do it. Let's pull that down. So let's do that whole nonsense cubed minus 4 times that nonsense again and square it. Computer doesn't mind that I'm asking it to do something ridiculous. That again plus 6, and I get over here negative 87942. Negative 87942. And if I go back again, there it is, negative 87942. So right there is one of my x coordinates of the max or min, and there's a y coordinate of a max or min. If I want to find the other one, all I got to do is change that to a minus, change that to a minus, change that to a minus, and change that to a minus. And so then I get 0.131483 and 6.0646. And so if I go up right there, I've got 0.131483 and 60646. So basically calculus has allowed me to sort of very quickly find the max and the min of those. Now, how am I going to know which one's a max and which one's a min? Well, we could just look at those numbers, but once again, let's use calculus. So what I want to throw in there is that okay, so let's look at that. Take the second derivative of that, y equals, let's put a little darker color on that. Let's do this one. Y equals 6x minus 8. Boom. Well, look at that. Right here, this is my second derivative. In this region here, the second derivative is, let's open that up. Let's move over. In this region here, the second derivative is negative, which means that the curvature of the blue line is negative, which means that it's bending downward. So if it's bending downward, this point here has to be a maximum. Right at that point right there, right there is where it switches, where the blue graph switches from having a negative curvature to having a positive curvature. So here it starts to get smiley. And then right there, so that means that that maximum right there has got to, or that point right there has got to be a minimum because it's bending up. So it's going down, but it's bending up. And so wherever it bends up, the max or min where it's bending up has got to be where it's got a minimum. And then our point of inflection, we haven't really talked about it all that much, but our point of inflection is right there. And we can use our equation to find that point of inflection pretty easily. set that equal to 0, and you're going to get 8/6, or you're going to get 4/3. So at x equals 1.33333, you've got a point of inflection. Okay, now I want to do one other one in this video here. So I just want to do y equals, I think I'm going to do x cubed, let's do 3x cubed minus 2x squared. Okay, so let's take the derivative of that, and we get we get y prime. So because the graphing calculator doesn't really like the primes and all that stuff, I have to sort of just leave it as y equals this and y equals that. So I sort of apologize, and you're going to have to sort of see through some of the limitations of the software. 9x squared minus 4x. Okay? So the question is, where does this equal 0? Well, this is going to equal 0 at, you can just sort of factor it out. Well, I didn't really mean to do that. And that graph didn't really do what I wanted it to do. Okay. I thought I knew what I was doing, but not really. Okay, I'm just going to do this. Y equals x minus 2 cubed plus 4. That's going to do what I want to do. Okay. So we could, just because I want to do this for you, y equals, I'm going to FOIL that out, x minus 2 times x minus 2 times x minus 2 plus 4. And so I'm going to, this whole thing is going to be, I'm going to replace that with x squared minus 4x plus 4. And then let me just do a new one. Y equals, that's going to be x cubed minus 4x squared plus 4x minus 2x squared plus 8x minus 8 plus 4. Okay, so then sort of cruising that down, that's going to be negative 6x squared, that's going to be 12x, and then that's going to be minus 4, and then I can take these out, throw a minus 4 on the end of that. And if I did it correctly, I should end up with the same function, and I do, so I did it correctly. Okay, so let's take that out. And so the question is where's the max and the min of this? So I want to find where the max and the min of this is, and so I just take my derivative. Y equals 3x squared minus 12x plus 12, and then I can factor a 3 out of that. So I can write it as y equals, well, I can, if y equals 3 times x squared minus 4x plus 4, well, then I can factor that into x minus 2 squared. So y equals 3 times x minus 2 squared. And so this has a max and a min at x equals 2. Well, how can it have a max and a min at x equals 2? Okay, so it's going to have a saddle point, which basically means, and so then let's look at the second derivative. So the derivative of this is going to be 6x minus 12. The second derivative also has a 0 at x equals 2. So basically what that means is that here my function is going up, 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 and it's got negative curvature. Here's my, let's make that a little bit darker. Let's make this, let's make that pink, and let's turn these off. Let's scroll back down and look at our function. So the blue is our function, the pink is the derivative of the function, and the red is the second derivative. So where the red is negative, the curve, the blue line is frowny face, so it's curving down. So even though it's going up, it's curving down. Where the pink line is positive, it's going up. So the pink line says that in this region, my blue line is going up. Then right there, it stops going up. But then the pink line says that over here the slope is still positive, so then it goes up again. So the slope of this line is negative. The slope of the blue line is never negative. Never negative. It can only be 0. So it's positive. It's positive. So like the slope of the blue line is positive. The slope of the blue line is 0. The slope of this blue line is positive again. And then we have here the curvature of the blue line is negative, so it's frowny face. The curvature is 0, which means that it has no curvature, it's just straight. And then the curvature is positive, which means it's smiley face. So it goes frowny face, going up to a frowny face, leveling off, and then it goes up again. And so that point right there is a point of inflection. Oh, well, it's a saddle point. So it's a saddle point. So let me just make a little note of that. Okay, you can find saddle points where the first derivative has a double root and where the second derivative shares a root with the first derivative. And so here, the second derivative has a root at x equals 2, and the first derivative has a root at x equals 2 twice. X equals 2 solves this, but it's like twice. Okay, and you can show that the two statements have to occur simultaneously. So, if the first derivative has a double root, the second derivative must share a root with the first derivative. That's what I'm saying. Okay, so that's that video.